Welcome to a Programming Languages virtual meetup. My name is Connor Hoekstra, and in this video we're going to be covering Chapter 4.3 of the Structure and Interpretation of Computer Programs. The table of contents for this chapter section are as follows. It's 4.3 entitled Variations on a Scheme, Non-Deterministic Computing. There are three subsections, 4.3.1, AMB and Search, 4.3.2, Examples of Non-Deterministic Programs, and 4.3.3, Implementing the AMB Evaluator. Word of caution, this is definitely, at least for me, was by far the most challenging chapter section so far. It builds upon the last section of chapter 4.1, 4.1.7, where there was modifications made to the ordinary scheme evaluator, which they ended up calling the Analyzing Evaluator, and the scheme interpreter that's built up here, which is called the AMB, which is short for Ambiguous Evaluator, is built on top of that. So unfortunately, I didn't go into too much detail of the last section of chapter 4.1. So in order really to grok the contents of this chapter, you need to revisit the last section of 4.1, understand the Analyzing Evaluator there, and then build on top of that in this chapter. With all that being said, let's hop into the contents of this chapter section. So the chapter section starts out by saying, in this section, we extend the scheme evaluator to support a programming paradigm called non-deterministic computing by building into the evaluator a facility to support automatic search. This is a much more profound change to the language than the introduction of lazy evaluation in section 4.2. So if you recall, the last chapter, section 4.2, we worked on a variation to the scheme evaluator that we did in 4.1, and that was for introducing lazy evaluation into the language. Here we're going to do the same thing, except, as I mentioned, not building up from the ordinary scheme evaluator, building off of the Analyzing Evaluator, and we're going to be adding something called non-deterministic computing to this model. The chapter then goes on to state the non-deterministic program evaluator implemented below is called the AMB evaluator because it is based on a new special form called AMB. We can type the above definition of prime sum pair at the AMB evaluator driver loop, along with the definitions of prime, and element of, and require, and run the procedure as follows. So if we input prime sum pair with two lists, 1, 3, 5, and 8, and 20, 35, and 110, it will return us a non-deterministic solution of 3 and 20, which when we sum those, we get 23, which is a prime number. The value returned was obtained after the evaluator repeatedly chose elements from each of the lists until a successful choice was made. And note that if you type in try again to the driver loop, you'll get a new prime number. And if you continue to do this, it'll return you prime numbers until it exhausts all possible primes from the given lists. So this is all from the beginning section. So at this point, we'll hop into the first subsection, 4.3.1, which is entitled AMB and Search. So the textbook reads, to extend scheme to support non-determinism, we introduce the new special form called AMB. The expression AMB with a number of expression returns the value of one of the n expressions ambiguously. For example, the expression list of AMB 1, 2, 3 and AMB with the symbols A and B has 6 possible values, which are enumerated below. AMB with a single choice produces an ordinary single value. And the textbook then goes on to state that we need to add this require procedure to our AMB evaluator in order to use it in the solutions that are going to take advantage of this sort of non-deterministic computing model. So at this point, I believe we're going to jump to the first exercise, which uses this require procedure, which is exercise 4.35. So it states, write a procedure and integer between that returns an integer between two given bounds. And the rest of the question is just stating that it gives an example of a procedure, a Pythagorean triple between, which can make use of this and integer between. But we don't need to really use that in order to solve this question. We just need the first sentence. So a possible solution to this is the following. So we have our procedure and integer between. There's a small spelling mistake there. There should not be the first R, and then two parameters, low and high. And you can see here we're setting a condition that low needs to be less than or equal to high, and then we have a recursive call at the bottom here. So we're calling A and B low, and then for high we are making a recursive call to an integer between 1 plus low 1 plus low, 1, so we're basically incrementing low and then high. So this is going to, one by one, give you the numbers between low and high until this basically predicate condition is no longer satisfied. This brings us to the second section, or subsection of 4.3.2, entitled Examples of Non-Deterministic Programs. This was my favorite subsection of the chapter, as it introduces a number of fun problems to solve that can really take advantage of this non-deterministic sort of programming model. So the first one we're going to look at, it's stated in the text, so this isn't an exercise, and it states the following. Baker, Cooper, Fletcher, Miller, and Smith live on different floors of an apartment house that contains only 5 floors. And then the problem goes on to state a number of conditions that we can use to solve which floor each of the individuals live on. So if we slide this off to the left and we put up a little sort of logic table, if you ever did logic puzzles when you were younger at any point in your life, you could typically see these visualized as like an upper or lower triangular matrix. This one is simple though, so we only need one grid. But let's one by one go through the statements and see if we can solve this. So the first statement is Baker does not live on the top floor. So that means we can X out floor number 5, which is the top floor, because Baker can't live here. Then we have the next statement, Cooper does not live on the bottom floor. So Cooper can't live on floor 1. The next statement, Fletcher does not live on either the top or the bottom floor. So for Fletcher, we can scratch out both floor 1 and floor 5. The next statement, Miller lives on a higher floor than does Cooper. So this is the kind of statement that initially seems like we can't get that much information out of it, but if you read into it closely, you can. So the first thing we know is that if Miller lives on a higher floor than Cooper, Miller can't live on the bottom floor, because that would make it impossible for Cooper to live on a lower floor. And because Cooper can't live on the first floor, we know Cooper has to live at least on floor 2, which means that Miller can't live on floor 2 either. And finally, because Miller has to live on a higher floor than Cooper, Cooper can't live on the top floor. So we can also get rid of floor 5 for Cooper. And then we have 2 final statements. So Smith does not live on a floor adjacent to Fletcher's, and Fletcher does not live on a floor adjacent to Cooper's. So if we combine those two statements, Smith and Cooper do not live on floors adjacent to Fletcher. So at this point, we sort of need to do some Sudoku mental math in order to solve this. So because Fletcher can only live on either 2, 3, or 4, let's sort of walk through each of these to see if they're possible. So if Fletcher lives on floor 2, that means that Cooper, because Cooper has the same options as Fletcher, either would have to be on floor 3 or floor 4. But because Cooper can't be adjacent to Fletcher, we know it can't be floor 3, which means that Cooper would have to be on floor 4. And if that's the case, because we know Miller has to be higher than Cooper, Miller would have to be on floor 5. But that would mean that Smith would end up adjacent to Fletcher. So Fletcher can't be on floor number 2. So that leaves us with either 3 or 4. We can rule out 3 right away for Fletcher, because if Fletcher's in floor 3, Cooper necessarily has to either be in 2 or 4, which is adjacent, which means that we know that Fletcher is on floor 4. And because of this, we can then put Cooper on floor 2. And from here, we're able to deduce that we've got floors 1, 3, and 5 left. And because 3 and 5 are both adjacent to 4, which is where Fletcher is living, Smith has to be on floor 1. And because we only have 3 and 5 left, and Baker can't live on floor 5, that means Baker is in floor 3, and Miller is in floor 5. So that's pretty fun. I love these kinds of logic puzzles, but this was a lot of sort of mental arithmetic that we had to do, and it would be a lot easier if we could just write a simple program to solve this for us, which is exactly what this chapter is teaching us. So at this point, we are going to skip over the code that the book shows you and go straight to the solution that asks us to modify that code, and then in the solution for that, we will take a look at the original code from the book. So the next exercise is exercise 4.38, which states modify the multiple dwelling procedure, that's the example we just looked at, to omit the requirement that Smith and Fletcher do not live on adjacent floors. How many solutions are there to this modified puzzle? So this is the code that the book shows us to solve this. We basically have in our let expression all of the 5 individuals that are going to have the same sort of values given to us by A and B, 1, 2, 3, 4, 5. And then we have a bunch of require statements or expressions that list out all the requirements. So obviously, all the floors have to be distinct. And then each of the following requires basically state or represent the information given to us in the word statement. And so at the end here, it's just going to print out each of the floors that the individuals live on in list format next to their names. And in order to solve this, all we have to do is comment out the condition that says Smith and Fletcher can't be on adjacent floors. And if we take a look at what this yields, we see that there are 5 possible solutions. So the order of these corresponds to the order of the individuals listed in the let expression. And note that I actually generated this from the next problem that we're going to look at, which is 4.42. 4.41, which is stating or asking us to write an ordinary scheme program to solve the multiple dwelling puzzle. So we previously used the require procedure, which is defined using the AMB special form, but in this one we're just going to use regular ordinary scheme to solve it. So what would a possible solution to this look like? So this is my solution. It actually looks pretty similar to what we had before, just slightly different syntax, as we don't have the require procedure. So at the bottom here, this is the key part. We've got our multiple dwelling, which doesn't take any arguments, and we first generate the permutations from the numbers 1 to 5. 6 is exclusive. And originally I used a Cartesian product, but then I realized when you are using a Cartesian product and then taking the unique values from that, that's just permutations, which is a procedure that comes with Racket. And then once we have that, we are filtering using a predicate, which is basically determining whether we have a valid list of floors for each of the individuals. So here, very similar to what we had in our multiple dwelling procedure in the AMB evaluator solution, let expression, I initially used car, catter, etc., but when you get to 5th, the cat-a-da-da-da-der doesn't exist. And I remembered that in Racket they have these convenience functions. And then once we have this, we just have a conditional expression. We reverse sort of the predicate not. So this was originally, we don't want Baker to be on the 5th floor, but here we can just set it up, reverse the not, so we get rid of double not equals no not. And if we end up with Baker on the 5th floor, we know that this isn't valid. So just for all of these clauses, when you negate them, just return false. And that means that if we run into these conditions, we're going to yield false. And if you can get through all of them without any of them yielding false, you're going to end up with a true solution. And if we do this, you end up with the correct solution. So pretty neat. And at this point, I believe we've got one more puzzle that's fun to work through that we're going to solve. So this one is called the Liar's Puzzle, and it says, solve the following Liar's Puzzle. 5 schoolgirls sat for an examination. Their parents, so they thought, showed an undue degree of interest in the result. They therefore agreed that in writing home about the examination, each girl should make 1 true statement and 1 untrue statement. The following are the relevant passages from their letters. Betty said, Kitty was 2nd in the examination. I was only 3rd. Ethel said, you'll be glad to hear that I was number 1, and Joan was 2nd. Joan said, I was 3rd, and poor Ethel was on the bottom. Kitty said, I came out 2nd, and Mary was only 4th, and Mary finally said, I was 4th, and Betty took top place. So the question asks, what is, in fact, the true order of the 5 girls? And so note that in the 2 statements that each person makes, 1 is true and 1 is false. So they can't both be false, and they can't both be true. So what does the solution look like for this? This, I just used ordinary scheme, although the chapters clearly wants us to use the require procedure and the AMB evaluator. But I decided to just modify the code from the previous solution. So here we are setting things up with a let expression that's very similar to what we had in the previous solution. And for our conditional expression, we are basically seeing, do the results of each of the 2 statements yield the same value? So if they're both true or they're both false, we want to return false, because they need to basically only have 1 true and 1 false. And if you can make it through, once again, all 5 of these statements, you have a true solution. And if we use the same format with that we did for multiple dwellings for the Liar's Puzzle, permutations, and then filter, you'll end up with the result. So Betty is 3rd, Ethel's 5th, Joan is 2nd, Kitty is 1st, and Mary is 4th. So pretty fun to work through these. I encourage you to do them. And it's neat to think that, like, I would never have thought that using these kind of logic puzzles, you could, in less than like 20 lines of code, code up a simple procedure that generates you the answer so simply. So pretty neat to see that this is possible. And at this point, we get to, in my opinion, what is the most difficult subsection of a chapter section of the book. So this is 4.3.3, implementing the AMB evaluator. As I mentioned before, this builds off of chapter 4.7.1, so make sure to revisit that. And we are going to very quickly go through all the adjustments. So similar to the pre-recording for Chapter 4.2, when we looked at what are the changes you need to make to the ordinary scheme evaluator in order to end up with a lazy scheme, we're going to go through all the changes, but rather quickly, we'll focus mostly on the AMB analyze procedure, which is needed to solve exercise 4.50. But I am definitely going to need to revisit both 4.7.1 and 4.3.3 together because, as I mentioned, this is, at least for me, was definitely the most challenging subsection that I've encountered in SICP so far. Hopping into the subsection, though, the chapter states, we will construct the AMB evaluator for non-deterministic scheme by modifying the Analyzing Evaluator of section 4.1.7. As in the Analyzing Evaluator, evaluation of an expression is accomplished by calling an execution procedure produced by analysis of that expression. The difference between the interpretation of ordinary scheme and the interpretation of non-deterministic scheme will be entirely in the execution procedures. The text then goes on to state a very important concept about continuations. So execution procedures and continuations. Recall that the execution procedures for the ordinary evaluator take one argument, the environment of execution. In contrast, the execution procedures in the AMB evaluator take three arguments, the environment and two procedures called continuation procedures. The evaluation of an expression will finish by calling one of these two continuations. If the evaluation results in a value, the success continuation is called with that value. If the evaluation results in the discovery of a dead end, the failure continuation is called. Constructing and calling appropriate continuations is the mechanism by which the non-deterministic evaluator implements backtracking. So this is extremely important. Continuations fall into the paradigm of CPS, which stands for Continuation Passing Style. This book doesn't go into too much detail of explaining what that is, but I believe there is a sort of, I won't say sequel, but a textbook that was written by, I could get it wrong, it might be Matthias Feleisen, and the textbook is called Elements of Programming Languages, and it has 2 chapters dedicated to continuation passing style. So I will include links to all the links that were shared in the meetup that happened yesterday, depending on when you were watching this, and one of those links is to the Amazon copy of that book if you're interested. So at this point, we're going to take a look at all the changes. So this is the analyze procedure that is used or invoked in the eval procedure from the 4.1.7 analyzing evaluator. And so this is where we left off if you're coming from 4.1.7. And the only change we need to make here is to slide this down and then slide in the AMB analyze expression here, clause. So we've got the AMB predicate, and then this is invoking the analyze AMB that we'll take a look at later. Here we have the AMB predicate that we just saw, and then the AMB choices selector. And of course, as the text mentioned, we have the AMB eval procedure, which is a replacement for the eval procedure that we had in our analyzing evaluator. That one only took the expression and the environment, but now we've got 2 extra arguments, succeed and fail, which are going to be the continuations that are going to dictate how our program evolves. We then have to replace the self-evaluating quoted variable and lambda procedures with the following. This is basically just adding the succeed and fail parameters. And then we're going to very quickly go through the next changes. So you have to replace the analyze if with the following. You have to replace the analyze sequence with this following piece of code. This is analyze definition. This is analyze assignment. And you'll note that the pattern here is that you'll see a bunch of fails and fails too. These are sort of governing how which path we're going to take. If we succeed, we're going to end up taking the succeed continuation. Otherwise, you can see here, this is the case where we take the succeed continuation. Otherwise, we're going to need to backtrack because we found a dead end, and this is sort of how we get non-deterministic behavior. We then have our analyze application, which here you can see is calling the execute application. Get_args is a helper procedure that's used inside analyze application. Execute application was the procedure that we just saw being called inside analyze application. And then here we get to analyze AMB. So this is the procedure that I said we'd pause at for the longest. So here we have a let expression cprox, which is basically just dropping the AMB from our tagged expression that has AMB as the first element of the list, and then we're mapping analyze over these. And then we're going to pass this to try next, which is defined internally inside this lambda. And you can see inside here, in the cases where we don't have any choices, we end up failing. Card choices is going to return a procedure, which is then going to take env succeed and this lambda, this failure lambda, as the arguments. And you can see here, this is the key where if we end up failing, we're going to end up trying or recursively calling try next and then cuttering down our choices. So this is sort of the body of where we're going to be working our way through the permutations of what's possible in the lists that are passed to AMB. And whenever you hit failures, you're going to end up just trying the next combination. So if you can understand this procedure, you are, I don't know, 40% of the ways to sort of understanding the AMB evaluator in its whole. And I think second from last is the driver loop, which we're not going to say much about, but this is definitely more complicated than the driver loop that we've seen before. This is because it's dealing with a bunch more cases. So at the bottom, you can see if we're not in the midst of an AMB evaluation where we have different possibilities, and you do try again, it's just going to return you there's no current problem to solve. And then everything above that is dealing with what to do when you get try again and when you have a new problem. And last but not least is the required procedure that we saw earlier in the text. Every time we enter the driver loop, or if we're not in the driver loop and we're setting up a procedure call, sort of literally, you have to make sure that you define the required procedure in the driver loop or the AMB eval literal call so that you can use it in the procedures that you are defining. And this brings us to our last exercise of the pre-recording, exercise 4.50, which reads, implement a new special form ramb that is like AMB, except that it searches alternatives in a random order rather than from left to right. Show how this can help with Alyssa's problem in exercise 4.49. So we're not going to do the last part. We're just going to look how what we would need to do in order to set up this new special form ramb, which is very similar to AMB. It's just randomizing the order in which we go through things. So these are the only changes that we need to make other than the clause that you would need to insert into the analyze procedure so that we could handle it. We have our predicate that's checking to see if we have a ramb expression, then the selector, which is doing the exact same thing as the AMB selector was doing. And then we have our analyze ramb procedure. And this is identical to what we saw before. The only difference is that we are shuffling the cprox before we pass it to our initial call of try next. So this will get you the desired behavior that the question is asking for. Is it the most efficient? I guess that depends on your implementation of shuffle. But for the point of trying to solve this exercise, it gets the trick done, or the job done, I should say. That is all I have for today. There is a Berkeley lecture that corresponds not to chapter 4.3, but to the last section of chapter 4.1, 4.1.7. That lecture is entitled The Analyzing Evaluator. I will link that in the description down below. But other than that, I hope you enjoyed this video. Don't worry if you found this chapter challenging. As I mentioned, it was the most challenging for me so far, and 2 or 3 other people in the meetup also said that it was by far the most challenging. So definitely a chapter that I'll be revisiting in the future along with 4.1.7. But all that being said, I hope you enjoyed, I hope you learned something, and I hope to see you in the next video. Thanks, and have a great day.